Okay, so this is a work with Bo Kui, Charles, Bahia, Bo Yang, Leo Guibas, Ying, and Drago. A little bit about the background. So I guess today people are all familiar with this kind of synthetic data generation or AIGC. Oh, yeah, CG. Yeah, so I just want to mention like in the autonomous driving domain, like a synthetic generation is also very important, especially in generating data for training and testing the AI, the autonomous driving stack. So given some like a multi-sensor data captured in the wild with partial view coverage, which is shown on the left, specifically the goal here in autonomous driving is we want to be able to create some complete shape assets, object assets from this kind of partial observation, and being able to inject the assets back to the scene to create some synthetic data for training and testing. So this task in general, at a very high level, creating 3D content, complete 3D content from partial observation is a very challenging topic in a community, and it's also very trendy these days. Here I just listed like a two work, previous work, Giraffe and EG3D, which has been published in the past 2 years, but there are many more like on archive these days. So most of the work, if you look at the data set they have been using, it's basically Celebrate FFHQ Concars data set. So the assumption in the data set are the objects captured at a certain distance with little occlusions. But this creates like a giant gap to objects we see in the real world, especially for autonomous driving. So for objects seen in the real world, we have seen a lot of occlusions. The objects can appear at different distances with arbitrary partial view coverage. More importantly, it also includes some long tail instances. We probably only see a few times. Yeah. I think let's think about maybe come back to the problem formulation, like from the perspective, probabilistic perspective. Given the viewpoint variable v, whether it's hidden or whether it's like a given as a conditional variable, as well as the object latent variable z, I think the most previous work, the what I call is like control. They use the control view formulation to generate the images. So here, our assumption is the object is visible, always visible, and maybe placed at a certain distance. But what we see in the real world is like this U-Haul car is occluded by another red sedan. So we have to consider this kind of surrounding context occlusions in this kind of probabilistic graphic model. So here, the occlusions node is actually affected by the object we are interested in, as well as the viewpoint and surrounding context. So this kind of misalignment between the data distribution in the wild and the probabilistic graph that have been used in the previous work actually lead to some difficulty in training like a generative model with adversarial training. So we took a different approach. Instead of generating this kind of occlusion surrounding context using like a decoder-only network, we instead take the like an encoder-decoder approach, which is also trendy. Basically we get inspiration from this like a giant generative model. So I think the key here is given the image, we use some encoder network or recognition model to infer the object latent in the first place. What the object latent can be further used to reconstruct the exact input we observe. So here, instead of generating the occlusions and surrounding context from scratch, we basically use the occlusion as a condition to basically force the network or force the model to predict only the visible pixels. In addition, we basically consider, feel like in order to basically cover all the distribution, especially long tails, a single Gaussian variable is definitely not enough. That's why we have introduced this kind of structure object latent in the 3D space. It's basically a low dimensional or low resolution version of the triplanar representation where each element is a discrete token, we also learn from the distribution. So our training of this kind of structure object latent, as well as the encoder decoder, basically has two stages. The first stage is just the feature learning. Given like an input image, we use a VIT encoder to extract the 2D patch tokens. And thanks to Philip, I mean, we use some cross attention to basically kind of like associate each of the 2D tokens into the 3D space. It's kind of a low-dimensional 3D space. Once we have this kind of triplan latent in the 3D space, we also apply an additional quantization step to convert the continuous variable into discrete tokens. This is for the second stage training I will cover later. Yeah. Once you have this kind of a triplan latents in discrete space, we also apply a decoder network, which is kind of style-based. We upsample the low resolution triplan latents into higher resolution triplan feature maps, apply a new renderer here. So here we generate the render mask as well as the render color. So since our data is always like have occlusions, we only supervise the focal or visible pixels. Yeah. So once we learn this from like a green triplan representation, so we apply this maskit, which is like iterative generation pipeline that's from Google research, conditioned on a scalar class semantic time of day information. So we can do this iterative like a triplan latent generation in this way. So once we generate the triplan, we just feed that to the pre-trained decoder. So in this way, we can generate arbitrary amount of even unseen assets conditioned on the conditioning variable like scalar class, as I mentioned in this picture. Yeah. So the data sets we have been used is basically we extracted thousands of objects from the Waymo open data set, and including the camera images as well as the point clouds of the objects. In particularly, we basically provide accurate registration for each of the camera rays and the light point clouds in the object century frame. Yeah, we plan to release the data set to the community. So here I want to show some visualizations of the generation quality where we learn like a vehicle GINA on the entire like Waymo open data vehicle category. Yeah, here are some like rotating vehicles assets we learn to generate from the entire data set. You can see some like a real SF muni buses if you live in the Bay Area. Yeah, I think this framework can be easily extended to generate like a semantic mappings, especially for this kind of, we can try to generate the dyno feature maps in this way. Yeah. We also have some in-house data set which contain a lot of long-tail trucks, construction vehicles. We learn a model on the entire data set, and we show that we can actually generate very nice results. Yeah. So all I showed in previous slides about like unconditional generation, but since we decouple the training into two steps, we can actually retrain the second stage with different conditions, like class condition, time of day condition, box condition, image condition. These can be very useful for simulation because you can actually create arbitrary like things with these conditioning variables. Yeah, here are more visualizations of the data set. And pedestrian benchmark. Basically, we believe to our best knowledge, this is the largest, most diverse data set for this purpose in autonomous driving industry, which we plan to release very soon. So yeah, you have seen the talk and all the results. I think there are certain limitations of the work, especially currently we see some generalization issue beyond the rigid object. And it's kind of model is kind of sensitive to the LiDAR 3D bounding box notation. It's also an interesting question: how can we do extension to field shot, and how to better model the view-dependent aspects? So finally, I will thank all the attendees from Zoom or from basically attending in person, as well as the organizers. Also, the Waymo team who contribute a lot to this the work as well as the collaboration with Google Research. Any questions?
Thank you very much. So we have time for a couple of questions.
Very nice talk.
Thanks.
I've seen the triplane used multiple times. Do you have any intuition why that actually works?
Oh yeah, I think that's a great question. I think we have maybe two versions of triplane. Triplane for rendering. I think that's basically we can use voxel grid, but I think voxel grid is too expensive to generate at the training time. That's why I think triplane is a good approximation. For the latent space triplane, we also actually in the paper we tried non-structured latent space. We show that I think with this kind of triplane in latent space, it actually learns much faster and generally much better. I think that basically reflect the underlying structure of the data we have. Yeah, that's a great question.
Any other questions? So does moving on to the triplanar representation limits the type of shapes that you can produce, or is there no limitation? Does it have to be convex?
Yeah, I think that's a great question. I think basically triplane, I didn't use just like 3 feature maps. It's basically 96 feature maps, like 32 per x, y, y, z, z, x. I think that's yeah, I would say maybe some very complex shape you cannot do in the triplane. Maybe you can do in voxel representation, but maybe triplane is yeah. You will see, like paper also has some limitation on generating the pedestrians. Like that might be the case, yeah. But yeah, basically we want to release the data set, so maybe the academia can also play with the data set. Yeah, so to have more findings, yeah, more benchmark. Yeah. Thanks for the good question.
Thank you very much. So let's thank the speaker once again. The next invited accepted